Okay, so we're going to cover periodic trends real quick. So remember, the three that we're focusing on for this class are radius, which is how big the atom is, ionization energy, which is how easy it is to become an ion, how easy it is to lose an electron, and electronegativity, how strongly atoms pull on their electrons, how much the electrons want to be next to those atoms. So we see this pattern here, right? This is the summary that we wrote down on our periodic table. As we go this way, atomic radius gets smaller, but ionization energy and electronegativity increase, right? That's what this arrow is summarizing. As we go down, right, the radius, the size of the atoms gets bigger, but the energy it takes to lose an electron and the affinity for electrons, or the electronegativity, the strength of electron pulling, gets smaller and smaller, okay? So that's the trend. Why do these trends exist? Well, it comes back to our charges, right? So if we look at these Bohr models, I do want you to have this on your periodic table. Know that period is the across, so this is period 1, period 2, period 3, period 4, and that groups are the up and down. So group 1, group 2, group 3, right? These are, group 13 and 14 are also known as like group 3A, 4A, 5A, 6A, 7A, okay? So, as we go across a period, we notice that the electrons are in the same energy levels, right? This is energy level 2, energy level 3, energy level 4, right? Energy level 1. So the main focus as we go across is going to be the charges in the middle, right? The nucleus, the positive charges are pulling those electrons in, right? Positive and negatives attract. So as we go across, right, the distance doesn't change too much, but the protons and the charge get stronger and stronger. And so this nucleus is going to pull on these electrons a lot harder than this nucleus is going to pull on this electron. And then this nucleus is going to be even stronger with that plus 10 pulling these electrons in. So as it pulls those electrons in, that second energy level shrinks a little bit. It gets a little bit closer to the nucleus compared to over here. So that's why the atoms are getting smaller as we go across. What about the electronegativity? Well, isn't that just the ability to pull on an electron, right? So plus 3 is going to pull on this electron a lot weaker than plus 6 will pull on these electrons. Plus 8 is going to pull stronger. Plus 10 is going to pull the strongest in this row. So as we go across, we're getting a stronger and stronger attraction to the electrons, which means harder and harder to remove them because they have a stronger and stronger attraction. So that explains why electronegativity and ionization energy both increase as we go across, okay? As we go down, the atomic radius is easy. We are stacking these electrons on bigger and bigger energy levels, right? So you have energy level 1, then 2, then 3, then 4. So there are more protons in here pulling these electrons in, but they're so far away that it's still a much, much bigger atom than these ones above it. So atoms get bigger and bigger as you go down the periodic table. Now, why do electronegativity and ionization energy get weaker as we go down? We see that there's a ton of protons in here. So there's a ton of positive charge pulling this outer electron compared to, say, hydrogen, for example. Well, remember, the other thing that affects the strength of charges is how far away they are. So hydrogen has a very weak nucleus, but its electron is super close to it. Look at potassium. It has a strong nucleus with 19 charges, 19 protons in it, but its electrons are way out in the 4th energy level, so they're really far away. And if you remember our electrostatics, distance has a stronger effect on the force, this attraction, than the amount of charge does. And so as we go down the periodic table, yes, it's a stronger nucleus, but the electrons are so far away that it gets weaker and weaker and harder to pull on those electrons. And so your electronegativity decreases, and your ability to become an ion, right, the energy it takes also decreases. They let go of these electrons much easier. So as we go down, bigger atoms, but weaker electronegativity and ionization energy. So some possible questions you might get for this would be like this one. Circle the atom in each pair that has greater electronegativity. So we're going to look at Ca and Ga, and we're looking at electronegativity. So we have Ca right here. Where's Ga? Over here. So electronegativity, so they're on the same period, right? So we don't need to worry about this one. We just need to worry about this one. As we go across, we know electronegativity increases, so Ga would be more electronegative, okay? So Ga would be the answer to that one. That's how we do it. Lithium or oxygen. Okay, let's do oxygen or sulfur. This is a good one. O or S. So we're still looking at electronegativity. So we have O right here, and we have S right here. So notice they're in the same group. So we don't care about this. We're just looking at the up and down now. I notice that as we go down, electronegativity decreases. That's what it's saying. As we go this way, electronegativity decreases. So sulfur would be lower electronegativity than oxygen. Oxygen's the stronger one. So it's asking for greater electronegativity, so I would circle oxygen. Okay, that's how we do that. Let's look at number 9 here. So rank the following elements by increasing atomic radius. So we're starting with smallest to biggest atoms, and we have carbon, aluminum, oxygen, and potassium. So I happen to add that here. So let's just go through and start by highlighting these different atoms so we can see where they're at. Carbon is right here, oxygen is right here, potassium is over here, and then aluminum is right there. Okay, so the first things first is I want to compare the elements on the same period. So I want to look over here real quick. So I want to find the smallest atoms first. Okay, atomic radius increases as we go down. So I'm going to look at the ones in the topmost row, the period. And then once I'm there, I have carbon and oxygen. Okay, well, atomic radius decreases as you go this way, right? So I'm looking for that smallest atom. So carbon is over here, so oxygen's actually smaller than it according to this arrow. So it's going to be oxygen, then carbon, and then now I can look at these ones, right? And this one, they're on different groups, so remember that's the really easy one. Atomic radius gets bigger and bigger as we go down. So because this one's up here and potassium's down here, aluminum is the next biggest, and then the largest of these 4 is going to be our potassium. Okay, that's how we would do that. All right, how would we do it? Same thing, but let's do it for electronegativity. So again, we're going to go from smallest to largest electronegativity, looking at these atoms here. Sulfur, which is right here. Oxygen, we just saw, is right there. Neon is right here, and then aluminum is down here. Okay, so same as last time. I want to start, again, I'm looking for the smallest electronegativity. So I want to start on the highest period. So I know electronegativity, is smaller as it goes down. So actually, I'm going to start on the lower period, right? Because I want to start with the smallest one if I'm going from smallest to biggest. So I'm actually going to look at this period first, right? Because these would be the least electronegative, right? It gets lower and lower as we go down. And then they're next to each other on the same period, so I need to look up here. Electronegativity gets bigger as we go this way. So sulfur would be more electronegative. So aluminum then is my weakest, right? It's furthest down and furthest to the left. So aluminum is first, and then sulfur. Okay. Now, remember, these are more electronegative up here, right? Electronegativity gets smaller as you go down, so up here it's bigger. And then now I need to see electronegativity gets bigger as we go across. So oxygen would be weaker than neon, right? It goes stronger as we go this way. So the next strongest would be oxygen and then neon. And that's how we would solve a problem like that. Okay? All right, thank you.